Now we're done with the rigid body kinetics part. We're on to the constraints part. And so our constraint here, the only constraint that we have to deal with is the pin between bodies 1 and 2. Okay, so I'm going to call this point P. And my constraint is going to say the acceleration at P according to member 1 has to be equal to my acceleration at P according to member 2. Okay, so let me start with member 1. Anytime you don't have a fixed point, you're going to have to use relative motion. So the acceleration of P relative to the ground is equal to the acceleration of P relative to the center of mass of 1 plus the acceleration of the center of mass of 1 relative to the ground. We already have a name for this thing. This is what we already called A1. Our acceleration of P relative to the center of mass is the circular motion equation. Our angular acceleration vector is 0, 0, alpha 1. The problem has to be given with angular velocities. You can't calculate those. So our angular velocity vector, it said it was at rest at this instant, so this is 0, 0, 0. And now the r vector goes from the center of the circular motion to the point that we care about. That is a vector from the center of mass to that point P. So that's 0.2500. So the acceleration of P relative to the center of mass is 0, 0, alpha 1 crossed with 0.2500. This stuff goes away. And you get 0, positive 0.25 alpha 1, 0. Now put in the relative motion part, and the acceleration of P relative to the ground is equal to 0, 0.25 alpha 1, 0 for z, I'll leave that off now, plus our variable A1, and so this is the vector A1x 0.25 alpha 1 plus A1y. So that's the acceleration at P according to body 1. Now we'll do it for member 2. This is just circular motion because there's a fixed point. And so the acceleration of P is equal to alpha cross r plus omega cross r. Again, omega is equal to 0, so that's going to go away. The alpha vector is 0, 0, alpha 2. The R vector is 0.50. So AP says 0, 0, alpha 2 crossed with 0.50 is equal to negative 0.5 alpha 2, 0, 0. And I'll leave off the Z. And now the constraint equations just say that those two accelerations we calculated for P have to equal each other. Those 2 points can't fly apart. So we'll say that A1x and then 0.25 alpha 1 plus A1y.
Sorry.
Has to be equal to negative 0.5 alpha 2, 0. We had 6 variables. Now this gives us our 5th and 6th equations. Our equation 5 says A1x plus 0.5 alpha 2 is equal to 0. And our equation 6 says A1y plus 0.25 alpha 1 is equal to 0. And now we have 6 equations for 6 variables. And we can solve that by reduced row echelon form. Yep.
I think earlier you mentioned for linkages with a fixed point to the ground, you would be using Rx and Ry equals.
Okay, that is only in the case of, so this was a case where the pin, it was a pure pin joint with the ground. So that acceleration was 0. I was talking before about if that point is in contact with the ground, but it can slide freely, like in a pin and slot or a frictionless contact or something like that. So we'll get to examples like that, but this one doesn't have it.
All right. And for those problems, the variable would just end up in our equations.
That's right. And you'd get one more constraint equation to deal with the one more force variable that you have. Yep. Any other questions right now? Yeah. Yes. Any other questions? Okay, that's all. Which one do you want?
For number 2. Number 2 by the end there.